You're listening to the Uptime Wind Energy Podcast, brought to you by BuildTurbines.com. Learn, train, and be a part of the clean energy revolution. Visit BuildTurbines.com today. Now here's your hosts, Alan Hall, Joel Saxum, Phil Totaro, and Rosemary Barnes.
Welcome to the Uptime Wind Energy Podcast. I'm your host, Alan Hall, in the Queen City, Charlotte, North Carolina. I'm here with Rosemary Barnes in Australia, Phil Totaro's in California, and Joel Saxon's back home in Texas. We've all decided that we're not going to talk about anything negative this week. That's good. Phil did have his pre-recorded rant. That's always good. So there is some dirt going on out there in wind, but I don't think we're going to talk about it this week because we just need a little bit of a break. Top of the order is this Chinese flying wind turbine that looks like a Zeppelin, and they have supposedly tested over in China the world's largest airborne wind turbine, and it's called the S1500. It's developed by Beijing's Saws Energy Technology, and it made in flight recently in Hami. It looks like a Zeppelin, and Rosemary, there has been a previous version of this that was around, but I don't think it went anywhere. But it looks like it's about 40 meters tall, about 40 meters wide, and about 60 meters long. So it's sort of this long tube, and inside of this tube, they have 1,200 kilowatt generators. So they're creating power up at altitude, and they have a cable that brings down all the power down to Earth. It's kind of like a heliostat and some of these other tethered systems. My question is, why are we trying that now, and especially in China where they have huge, massive wind turbines being built? Why this?
Yeah, I don't know. I often question why China makes certain decisions with the investments they make, because they have invested in a whole bunch of out there technologies as well as dominating most of the mainstream ones. And what I usually come up with is that they've got a try everything strategy. Very, very similar concept came out of MIT. I think that they developed it originally as a power generating thing, basically just based on the idea that wind speeds are way higher the further up you go. So they want to get up into those really high wind speeds that, way higher than what a tower can reach for a traditional wind turbine. And yeah, this original concept that I saw out of MIT, originally they were planning to use it for power generation. Then I think that they pivoted to telecommunications. And then I believe that they pivoted to not doing that anymore. So I haven't looked at it recently. Could be that I'm a little bit out of date on that, but it is interesting to see a concept picked up that, I don't think anybody would really say that was the most promising of all the different kinds of airborne wind. So it's interesting to see that that's the one that's been picked up. I think it's got some promise in that it's true that the wind resource is much better at high wind speeds, but there are a whole lot of challenges that need to be overcome. So it's not yet, I would say, sure whether any of these technologies are ever going to go anywhere. We're kind of at the point now where some companies are ready to find out, but it's definitely not taking over the world anytime soon.
Yeah, I was gonna say, Rosie, I tend to agree with you. There's the one I'm thinking about, Alan, it was containerized, and it was like it had a winch. You let the thing up and went up to higher altitudes. I think there's too many moving parts to these solutions to be something that's going to be done at scale. I think there's a great use for them in, say, I don't know, military operations or disaster response. Those kind of things, or very remote areas where you can't get anything else in, like a Caribbean island or some crazy thing like that. I think there's possibility there. However, to do this at scale, I just don't see it, right? This is by far the biggest one I think I've heard of, 1.2 megawatts. That's a lot of juice, right? That's creating a lot of energy. So I think that you can see this like, oh, we're trying to go to scale with this thing, but what's the practical use? I think, Phil, you actually said it before off air. Like, this is a solution looking for a problem almost.
Yeah, and what's funny to me about this is there's a couple of things here. One is what you just mentioned, Joel, like the economies of scale on doing this as some kind of displacement to conventional power generation is just completely impractical because we have so much infrastructure in place that's not associated with airborne. But we actually looked at, I want to say like 12 years ago as a company, we did the math on whether or not this type of technology made sense to use in, like islands or displacement of like diesel generation, basically, uh, places like Alaska or the Caribbean, like you said. So the math came out like if the price of oil is above something like $120 a barrel, then a solution like this makes sense. Otherwise, you're probably better off, especially now, because again, when we did this analysis, it was years ago, but batteries are easily more dispatchable now. The technology, this is one of those things, like you were saying, like, yeah, the technology works and you can make this like a TRL-9, but for what? Like, nobody's going to pay for this.
I don't think that they're up to TRL-9 yet because there's some, like it works and they've done autonomous operation, like in steady state operation. They've done some autonomous like launches and I don't know what's the opposite of a launch, pulling back in. You can't just stay up there through any kind of storm, right? So they have to be able to launch and retract, land, undeploy. You have to be able to do that autonomously if you're going to imagine, this having any kind of scale. And I think that, autonomous launch and landing has been done, but not in all conditions. At least last time I looked into it deeply, that was the last bit that was left. It's like, it can be done autonomously in good conditions, but not bad ones. So I think that there's still some proving out to go. And I think that Phil, you raised a really good point that it becomes like the further that other technologies develop, the less likely it is that airborne wind can catch up. And also that people like those early markets are going to want it. Now, islands, obviously solar panels are already deployed on a lot of islands. And then when you do have batteries so cheap that you can start to build up a whole day, a couple of days, a week worth of batteries would probably not be a totally non-comparable cost to the airborne wind. And also just so much less maintenance required, so much less that can go wrong.
There's one thing I wanted to touch on here that we skipped, we breezed by it because we talk about these things all the time. But for people that aren't used to R&D or aren't used to technology development, when we mentioned TRL-9 on the show here, Phil mentioned it, Rosemary mentioned it, that is a scale TRL-1 through TRL-9, and it was developed by NASA a long time ago. But basically, TRL-1 means concept and idea, all the way through 2, 3, 4, 5, 6, 7, 8, 9. 9 means commercially ready. We're ready to roll with this product as a thing. So when we say one of those levels, that's what we're referring to.
The United States had something very similar, or it still does, I think, along the East Coast. They put up aerostats around Washington, D.C., and they had a little radar underneath them so they could look over the horizon. So along the East Coast, there are these big, massive aerostats. And I don't know if you recall or not, but several years ago, probably 10 years ago now, they had one of those aerostats break loose in Maryland. And that cable that holds it to the earth is conductive. So every power line it came across started creating shorts and blackouts along its pathway until it finally crashed in Pennsylvania. I think they had an F-16 chasing it for a little bit once it broke free. But I remember that happening and thinking, man, that is a really difficult engineering design to create something as big as basically a blimp-sized piece and have a cable and have it hold it for eternity.
That's one of the biggest challenges, aside from the autonomous operation. One of the biggest challenges is just the materials properties of the cable itself, because the tether to get it, obviously it has to be conductive because the electricity has to travel through it. That's the point. And then, to reach the really good wind speeds, you have to be very far above the ground. I mean, you would want to go, like, what's a jet stream is like a kilometer up or something. So, that would be ideal. But at least, several hundred meters, and just the pure weight of that cable you have to then, like all of the lift that you need to keep in the sky to support that cable is all just coming off, being subtracted from the lift that is going into generation. So it's really tricky.
I did work on one of those designs for a cable years ago. You'd be shocked how small those cables are for as high of altitude that the balloon would go. So it's maybe about twice the size of your thumb, at least my thumb. And it's just full of really strong material plus power in it. So if anything kinks or goes wrong in the winding process and you damage that cable, it's a big deal. But if you do create a weak spot in it, your whole design floats away. Chaos reigns.
The other thing is that that's why they want to try the technology with the shroud design, because that obviously increases the rotor induction and everything, like Rosie was talking about before. The problem, though, with it is it's like, so theoretically you could put it at a lower altitude with lower wind shear because you're getting that acceleration. When they've done these designs, though, on shore, because there have been a number of companies that have tried doing shrouded turbine designs, it ends up increasing the fatigue load on the blade root to such a degree that the blades end up shearing, and you lose all the benefit of the shroud. So
Yeah, with ground-based ducted wind turbines, it's like almost like a little cheat, because you can get higher efficiency and beat the Betz factor, which is the theoretical limit for how efficient a wind turbine can be, a horizontal axis wind turbine can be. But it's just trickery because the shroud accelerates air from a bigger, like it's capturing a bigger surface area. The energy doesn't come from nowhere, so it's you can get the same effect by just having a bigger rotor, right? And then instead of a bigger rotor, you've used extra material to make the duct or the shroud. And so it's, if they use the same amount of materials, do you actually improve anything? You can get a better efficiency number, but you're not going to get a better cost effectiveness. And in any of the more advanced ducted designs that I have seen, they always end up using more material in the duct than they would to make a bigger wind turbine. If it's way up in the sky, why are you limited on the diameter that it can be? So it's I'm not sure. Aside from the fact that they want the buoyancy from the blimpiness of it, so they might as well make that into a shroud, I guess. If they're not using any extra material to make the shroud, then sure. But in general, ducted designs, they work, and depending on how you're calculating efficiency, they can be more efficient, but they're not more cost effective.
As wind energy professionals, staying informed is crucial and, let's face it, difficult. That's why the Uptime Podcast recommends PES Wind Magazine. PES Wind offers a diverse range of in-depth articles and expert insights that dive into the most pressing issues facing our energy future. Whether you're an industry veteran or new to wind, PES Wind has the high-quality content you need. Don't miss out. Visit peswind.com today. In this quarter's PES Wind Magazine, a lot of good articles. You need to go download it at peswind.com. I want to highlight an article I've been reading about, because this ties into things that Rosemary has been talking about in regards to steel and steel manufacturing, that it's very carbon intensive and CO2 intensive. And there's been a number of efforts to use electric arc furnaces to reduce the amount of CO2. And when you do that, you use recycled material you throw back into the mix to bring the carbon into play. But NLMK DanSteel, which is based in Denmark, makes the heavy plate steel it's used in wind turbines. They've been doing it for a long, long time. And the article on PES Wind talks about the complexities of doing that today, because we're asking wind turbine towers out in the ocean to do more and more and more. We're putting more weight on top of them. So any sort of grain defect can become catastrophic over time. So the amount of effort going into the steel plate and the technology that's going into making that steel is exponentially higher than it was even 10 years ago. And Rosemary, I know the effort to decarbonize steel has been there for a number of years, but NLMK is already starting that process. And I think it's really interesting to see it and see those pieces of steel that are using less or emitting less CO2 now being put out into service. It does take a very specific process, though, right, to do that.
Yeah, I don't know if you saw it, but I actually got to tour an electric arc furnace when I was in Sweden earlier this year. So that was really cool. We didn't talk a whole lot about like what I was there mostly to see. It's the world's lowest emissions steel production. So when the electricity price was low, they would make hydrogen and then burn that. They burn it immediately. They don't store it anywhere. They make it on site and then use it immediately. And then when the electricity price is high, then they're using propane. So it was kind of like a more economical way to retrofit a facility to be lower emissions. But it was such a cool thing to experience. It's, like a lot of the decarbonization things, like if you're in your home, it's like putting solar panels on a roof and a battery in the backyard, and you don't really, like, it doesn't feel that challenging. At least in Australia, it really doesn't feel challenging. Electric car is nice to drive, plug it in at home. You never have to go to a petrol station. It's all good. But then when I was in a steel facility, it's like, like you're standing 20 meters away from this molten steel and, just the weight of it. They're just like throwing around this like red hot steel, throwing it around like it's a noodle, rolling it. And yeah, just literally just throwing it around, grabbing it with claws and throwing it over there. And it's like the weight and the heat, it's just so obvious how much energy is used. But that is an electrified process also. So, even then it is still quite similar.
Rosie, do you think this is, okay, so I'm just going further down the path of what NLMK is doing here in this decarbonization of steel production. Because the steel production industry is like, it's not like cement, where cement is one of the highest energy users in the world. But steel uses a lot, and that's why there's an effort to do this. Can you see, so in this electric arc furnace process, is there a possibility of these things having, say, behind the meter wind backed up by batteries or behind the meter solar? Like, can that produce enough power to run one of these plants, or enough constant power? Because I imagine these things need on-demand power now. Can that happen, or do they have to be hooked up to the grid?
I don't know about behind the meter, because that's just, like a whole lot of power, and any one wind farm or any one set of solar panels is going to be quite variable. So I don't see that it would make sense really to separate from the grid, which can combine, a lot of different sources, and its whole operational existence is geared around being very, very, very reliable. So I'm not sure. I mean, it's one of those things that I guess as the cost of batteries comes down, then you can start seeing people probably inch closer to that themselves. But I can't really see why you would need to be off-grid. I'm sure there's lots of steel plants with power purchase agreements out there, with individual wind farms.
Yeah, what's the demand? Did they tell you what the demand is? Like, what is peak power usage? What are we using?
I didn't talk about it in that one, but I mean, electric arc furnace it's a very normal technology, and it's something that's been around since way before anybody cared about the emissions, CO2 emissions of steel, because it's very cost effective to take existing steel and just makes a new kind of steel product out of it, compared to taking dirt and trying to turn that into iron and then steel. It's a lot more cost effective. So to the extent that we have enough steel scrap that's from steel use that's being retired now, you would obviously go with that for everything you can. But at the moment, we're still, as a planet, we're still using more and more steel every year. So it's definitely not the full solution, but it's a part of it.
Did they make you leave your wallet and watch behind when you went into that arc furnace area? That's what happened when I used to work for Alcoa years ago, because the arc furnace is there.
The arc furnace wasn't on. They do a weekly cycle, so they shut down every Friday, and they kind of shut it down in order, because so the arc furnace had already shut down for the week, but the rolling was still going on. But it was kind of good because I could get right up to the equipment. You can't stand very close to it, obviously, while it's operating.
So, couple of things. First is the companies that have signed PPAs for steel production offtake, they've actually said that they're not doing 100% of their power demand because they still have to, like, there's a certain amount of base load power that they need, which they're actually taking from renewables instead of taking from some other base load power generation. But they still need to have like a peaker capability from the utility company that they're getting power from. Satzinger in Germany signed a PPA like that. There's another company in Scandinavia somewhere that also did that, like late last year, I want to say, or early this year. So there's a couple of companies that are doing that. The other aspect of this that I find fascinating is the fact that when you make a wind turbine tower, it contains what we call a specific type of detail category of the steel. So it's a certain grade and a certain thickness to it. What's basically going on with the evolution of this kind of technology, and what's so fascinating about it, is that you can now make things cheaper, faster, and thinner than you ever could before using this type of process. So there's less carbon, it's cheaper, it's faster, it's better, it's everything. That's what's actually really kind of cool about this and really fascinating to me.
And Joel, they're making plate about 10 inches thick. That's amazing.
That's crazy. While we've been talking, I'm curious about some numbers here, so I went and kind of just did a little bit of basic math, and this stuff is probably going to ring true to a lot. But a 70, they rate these electric arc furnaces in tons. So a 70-ton electric arc furnace, when producing 500,000 tons of steel per year, the annual power consumption would be 190 million kilowatt hours. Wind farm operating at 40% capacity is a 54 megawatt wind farm dedicated to this one steel factory. So that's like 36 GE15s just to power this one steel factory for the year.
One furnace.
One furnace outputting 500,000 tons, one furnace.
It's impressive. And if you want to be even more impressed, you want to download the latest quarter's PES Wind magazine, peswind.com. A lot of great articles, a lot of people that we know in there this quarter. Download it. It's free. A lot of good stuff in there. Are you worried about unexpected blade root failures and the high cost of repairs? Meet EcoPitch by Onyx Insight, the standard in blade root monitoring. Onyx's state-of-the-art sensor tracks blade root movement in real time, delivering continuous data to keep your wind farm running smoothly and efficiently. With EcoPitch, you can catch problems early, saving hundreds of thousands of dollars. Field tested on over 3,000 blades, it's proven reliability at your fingertips. Choose EcoPitch for peace of mind. Contact Onyx Insight today to schedule your demo of EcoPitch and experience the future of blade monitoring. Well, what if we told you that wind turbine blades could last 50% longer than their intended lifespan? Rosie would say, that's crazy. Well, ORE Catapult has been working with RWE on a breakthrough testing program. So what they have done is they've pulled a 20-year-old blade from one of RWE's harshest onshore wind sites and replicated real-world conditions. And they did it with 11i devices, Joel. And they simulated the aging process. And they successfully compressed 1 year of real-world impact into about 48 hours. Doing that allows you to then rapidly test blades for lifetime extension. Sally Paxson, who is the principal validation engineer at ORE Catapult, called this potentially, quote, a breakthrough moment for the wind industry, unquote. And I would agree with her.
What's awesome is that they're improving the reliability of the blades, but this is also fascinating for the companies that repair blades, because anytime you make something, cheaper, better, higher quality, less repair work equals less revenue for them. So they're not going to like it that much.
I'm going to throw a red flag on this study. I like the 11i technology, and I think it's really good because I've seen it work, right? Bill and the team over there do a great job. However, all of the blade conferences, all of the blade knowledge, all of the experts that I've talked to over the last 5 years, everybody basically has the same synopsis of the blade industry. 20-year-old blades, yes, they were tough. They were designed tough. They are going to last a long time. I don't care about those that much. I expect those to last 30 years. It's the new blades that I'm concerned about. Those are the ones that I don't believe. So if you're going to do this test, again, I'm throwing the red flag. You're going to do this test, do it on a 1-year-old blade. Do it on a brand new design we're installing today. And I bet you it won't last 30 years.
Well, that's the question, right? I think the all the ESIG groups and the DNVs and ULs have to be wondering, like, okay, now what? Because the certification test that Rosemary's been involved with in terms of blade qualification, is that real? Because that test is supposed to show the blades last 20 years if they do these series of tests, right? And now ORE Catapult's coming back and saying, we have a way to really hone in on it. I think lifetime tests could get much more advanced, I imagine.
So in the early days of the wind industry, when they started making blades out of composites, they had huge safety factors, or probably safety factor isn't the right way to think about it, because the safety factor itself has probably not changed, or not changed much since those days. But what they used as their material properties, that, you know, the values that they would put in their design codes, they were incredibly conservative. You know, they didn't know exactly how strong it was. They didn't know exactly what fatigue behavior would be like over decades. We've adjusted the materials properties. So now it's much closer to what it really is. But the problem is that then we've rightfully reduced the buffer in those kinds of areas, but it used to also kind of compensate for a bunch of other things that we didn't know that well, like manufacturing defects and like all sorts of funny operating methods or weird things that can happen. That was kind of all included in that fudge factor. And now that we have really, you know, come down, you get to the point where, yes, you can pass a certification test, but then when you get out into the real world, things don't happen exactly the same way every time. And there's, you know, like little shocks from the sudden gust of wind or some turbulence that you just behaved in some sort of way that you didn't expect, or, you know, like breaking loads. All these sorts of things can start to then cause failures.
So let me ask a question on this. Is the fact that we started moving away from, you know, kind of traditional composite to start including carbon, you know, basically everybody wants a longer blade with less weight. We had to start introducing carbon to be able to make that possible. Is it, you know, the carbon protrusions are part of the problem, or what's really kind of behind this?
I mean, carbon protrusions are part of the solution and then part of the problem as well. You know, they solved some things immensely and introduced new damage modes, failure modes, which you would say for any kind of new technology. I don't think it's all to do with carbon. I see plenty of interesting failures in all glass blades. It's to do with them being longer, I think, definitely. Like composite materials actually don't like to be thick. The thickness of just even fiberglass in a wind turbine blade is like really unusual for, you know, I was doing my PhD 13 years ago I started, and at that time, like thick composites, that's an area of research, and what counted as thick then is not as thick as what we see in wind turbine blades all the time. And it's not, these aren't being made under lab conditions, you know, so there's just a lot more things that can go wrong and not be discovered in the factory. You know, when you have a small blade, defects are more visible from the outside and from standard non-destructive testing techniques. So yeah, now they can kind of be a lot more hidden, and you might not learn until you've already got, you know, 5,000 blades out in operation.
I know this is a factor of economics, but this is one of the troubles that I have with standards, certifications, and all these things. Just what you said earlier, Rosemary, is the testing, right? So everybody's seen a test rig. If you're listening to this podcast, you've seen a blade test rig. It sticks the blade out. You're going to do some flapwise. You might do some oscillations. You might do some edgewise. Great. However, there is not a test stand in the world that can simulate centrifugal forces, gravity loading, aerodynamic loading, and those are major things that happen to these wind turbine blades all day, every day. So the answer to me is install them, run them for a year or two, figure these things out before you build 5,000 of them.
Yeah, but they do. But the problem is with any kind of certification is you're testing one thing, one example of something that's going to be serially produced with all sorts of random distributions. And in some ways it's conservative because it's your first blade and you probably haven't figured out how to make them that well. But on the other hand, you've made it really slow and everyone's paying a lot of attention. I don't think necessarily people are making it differently because they know it's going to be tested. I never saw that, but definitely everybody's paying attention for the first few blades because it's not become second nature anymore. You know, you're still reading the work instructions carefully and engineers are still there supervising everything. So yeah, you just can't get the statistical variation in a full population of blades by doing one test.
Isn't the 11i sensors that were used during this process, I assume, to show aging, if they're installing 11i's IMUs, Joel, that's basically what they are, is like an IMU.
Multiple ones in each blade.
You can detect different modes of vibration and how the blade is moving over time. If you can do that at some reasonable scale, say it's even 1% of the blades that are out in service for a particular farm, why wouldn't you? Because the lifetime issue is going to come up at some point. You would be able to tell if the blade has changed vibration modes or whatever else these structural engineers are doing. You would be able to see that over time. And I'm guessing that's what they're doing at ORE Catapult, is looking at structural changes that would occur naturally over time in the aging process, and they can accelerate that, and that's how they're validating it. But the same token, you can use that same technology to look at existing blades to predict what the lifetime of the blade would be.
It's another thing with like Rosemary's saying, though, when we're talking about this, we have to introduce the conversation of statistics, populations, samples. What are proper statistics? What do they look like? How do you test for them? Because if I'm a big operator or a small operator, I don't care, or a consortium, this is what it should be. A consortium of operators gets together and says, hey, we buy a bunch of these type of turbines between the 5 of us. Why don't we force this OEM to put these sensors in here on 5 of your turbines, 5 of mine, 5 of mine, 5 of mine? That would be great. And then we would have a picture of what's going on. However, here's the practical problem there. If you've got 500, we'll throw this out there. GE2X, we look at a ton of them. 127s, GE2X 127s. If you got 500 of these, the chances are those 500 turbines, 1,500 blades, came from probably 8 different factories, from 3 different manufacturers or 4 or 5 different manufacturers, and they may be any of 10 different versions from A, A1, A2, B2, B3, C1, C2, C3, and now we've even seen Gen D. So all of the results you're going to have to repeat for every one of those generations of that same blade. Like it's a problem that we have in wind that is a very unique, because we're doing things in serial production like we talk about, but the serial production changes so much. There's so much variability that to get statistically meaningful data is tough.
Yeah, but the cost is relatively low.
The cost that's relevant is not even so much the cost of the sensors, it's the people to manage the data. That's what I found. When I was always like, why can't I just install all of the sensors and just record all of this information and give me all of the SCADA data? And they're just like, no, we can't. We can't manage that. And it's one thing to do it on the prototype. I would. I could just install a separate system and manage that on my own. But if you want to do it operationally, then that's the biggest challenge. I mean, these OEMs are all, they want to hire the fewest number of engineers possible, right? Because they've got to keep costs down, and I don't think there's enough human power to be this smart across the board, unfortunately.
Joel, this goes back to the issue in the industry that we've had absolutely forever, which is the OEMs have some, but not necessarily all of that kind of data, because they obviously haven't outfitted every single turbine with sensors, but they are the ones that hold all the keys when it comes to what blade was manufactured where, what gearbox was manufactured where, because that's also a consideration too, just talking about general things. But so from the standpoint of the owners and operators, they're maybe not even going to have visibility to some of that kind of information. Even if they retrofit a sensor platform onto the turbines that they own, that may give them visibility, Rosie's point notwithstanding, doing the data analysis and all that, and the resources and money that's necessary to commit to that. But there's a missing piece that the OEMs are just fundamentally unwilling to share, We've been begging them for 20 years to let's do a project together where you give us some access to that type of information for purposes of benchmarking this, that, and whatever. Like, hey, you think you're better than Vestas? Then tell us, GE, how you're better than Vestas. Let us see some of your data. We don't need all of it, but some of your data. They won't even do it. Not even a little bit.
So, I mean, what it would take in my mind, and this is a macro thing, but what it would take in my mind is a consortium of people in the industry that are saying, okay, enough. We got our insurance company together. We got a finance company together. We got a couple of operators together. We're going to put together what would we call a JIP, a joint industry project. So everybody devotes a little bit of resources to it, and we stare at an OEM and say, we're not buying any more turbines until you give us some of this data or let us instrument these things.
I reckon that's the path through. If insurance companies can say, this is costing us too much and start offering a discount to clients that have this kind of monitoring, then I think that will, create a big enough pull to get this happening because, maybe the OEMs can see they can charge more for a product that has this because they just never want to include sensors. Even, just operationally, when I want to, get my client who owns a wind farm to, stick a sensor somewhere that's totally not affecting any structure, doesn't need to get into SCADA or power, it's solar powered and remotely monitored, they still often say, no, you can't do that. And it's, to a turbine that my client owns. So they just hate to allow anything at all. It's so irritating and so senseless because it's actually preventing the industry from maturing in the way that it would need to be future-proof as a long-term major technology.
And here's what's interesting is in industries like automotive, there's been a mandate. In industries like aerospace and aviation, there's been a mandate for that kind of transparency. There has not been a mandate. And going back to Rosie, your question, why do the insurance companies not have the power of mandate through, the insurance? It's because they're not actually backstopping every single thing that goes on out there. The only way we're going to get access to the type of data that we want, that we're all talking about right now, that's going to solve these problems and help move the industry forward, is through some kind of mandate.
That wraps up another episode of the Uptime Wind Energy Podcast. Thanks for joining us. We appreciate all the feedback and support we receive from the wind industry. And if today's discussion sparked any questions or ideas, we'd love to hear from you. Just reach out to us on LinkedIn. And please don't forget to subscribe so you never miss an episode. For Joel, Rosemary, and Phil, I'm Alan Hall, and we'll catch you here next week on the Uptime Wind Energy Podcast.